everyone, we're in chapter 5 and we're going to start talking about polynomial and rational functions in this chapter. And we're going to begin with quadratic functions in section 5.1. So in this section, you will be able to recognize characteristics of parabolas, which are the graphs of quadratics. You're going to understand how the graph of a parabola is related to its quadratic function. You are going to determine a quadratic function's minimum and maximum value. And you're going to solve problems involving a quadratic function's minimum or maximum value. All right, so let's start by looking at the characteristics of the graph of a quadratic. So again, the graph of a quadratic is called a parabola. All right, so let's start at the top here. So the graph of a quadratic function is called a parabola, which is a U-shaped curve. Now, you've seen this type of curve before because we talked about the different parent functions in our toolkit, and the basic quadratic function was one of those, and it was a parabola, and then we saw them again when we were doing transformations. So you should be very familiar with this shape, and this shape is called a parabola. Now, there are different parts of the graph. They're all labeled on the graph, and then they're explained over here on the left. So the first thing that we're going to talk about is the vertex. So the vertex is the turning point of the graph. It's where the graph changes directions, okay? And so you can see that point right here, the vertex. So again, that's where the graph changes direction. Next, using what we know that the vertex is where the graph changes direction, that means that if a parabola opens up, as it is on the right here, that means that the vertex represents a minimum value of the function. So if you think about it, if you look at this graph that opens up, the absolute lowest point of this graph is the vertex. The graph doesn't go any farther below the vertex. So that vertex is in fact the minimum point. So if a parabola opens up, then the vertex is the minimum. That means if a parabola opens down, guess what? It means that the vertex is the maximum. And let me just draw an example on the right here. Here's a parabola that opens down. Here's the vertex. You can clearly see that the vertex, this is the highest point on this graph. So that would be a maximum. Now we also have something called the axis of symmetry. Okay, so parabolas are symmetric. So that means if you split the parabola down the middle, the left side mirrors the right side. And the mirror that I'm referring to is this axis of symmetry, which is this red dotted line that I'm now tracing in purple. Now, it is a vertical line. You don't always see it drawn through parabolas, but it is there. You can label it, and sometimes I'll ask you to label it, but it's a vertical line drawn through the vertex, and again, it's called the axis of symmetry. If you will remember, if you have a vertical line, then the equation of that vertical line is just x equals, and then whatever the x coordinate is, because every point on a vertical line, every single point on a vertical line has the same exact x coordinate. So in this case, our x coordinate looks like it's 1. So the axis of symmetry is x equals 1. You wouldn't just say the axis of symmetry is 1. the axis of symmetry is an entire line, so you define it as the equation of that line, which is x equals 1. Now, you'll notice that there are two other things on here that we did not discuss on the left here that are labeled on the right, and that would be our y-intercept and our x-intercepts. All right, so y-intercept, that is where the graph crosses the y-axis. This is something that should be reviewed. And so it crosses the y-axis here at 0, looks like -3. Okay, so this is where the x equals 0. So the x equals 0, that's where you're going to find the y-intercept. Okay, so and you look at the point, it's 0, -3, the x-coordinate is in fact 0. Now, what's nice about the y-intercept is if you find the y-intercept, then you know another point, because you can use the fact that this parabola is symmetrical and that each point on the left has a mirror image on the right and vice versa. You can use that fact to find another point. If you look from the axis of symmetry at x equals 1. If you go to the left one space, you are at the y-intercept. If you go to the right, you're at another point. So you can always use that to help you find a second point. So there's also a point at 2, -3. All right, then we have our x-intercepts. And some parabolas don't have x-intercepts. If it doesn't cross the x-axis, then it's not going to have x-intercepts, but if it does, then it does have x-intercepts. So the x-intercepts, that's where it crosses the x-axis. This is where the y equals 0. These x-intercepts are also called the zeros of the graph. The zeros of the graph. So if it asks you to find the zeros, then that means you're finding the x-intercepts. And to find the x-intercepts, you set the y equal to 0 or the f of x equal to 0, and you solve for x. So those are the characteristics of a parabola. So using those characteristics, let's determine the vertex, the axis of symmetry, the zeros, and the y-intercept. So let's start with the vertex. So the vertex is where the graph changes direction. So we can see it's right there, and that looks like that's the point, -1 up 8. -1, 8. All right, so if you know the vertex, then you definitely know the axis of symmetry, because if you'll remember the axis of symmetry, which is not drawn on here, but I'll draw it, it's the vertical line that goes through the vertex, and the equation of that line is x equals, and then what is the x-coordinates of all the points on that line? Well, it's the same as the x-coordinate of the vertex because it does go through the vertex, so it's x equals -1. All right, next, let's find the zeros. So the zeros are the x-intercepts. So we have one here and one here at -3, 0, and at 1, 0. So that means my zeros are x equals -3 and x equals 1. And then last, they want us to find the y-intercept, which there's only one. So the y-intercept is right here where it crosses the y-axis. That's the point 0, 6. So that's what we're going to write. It's just 0, 6. And then I do want to show you that it has that mirror image point. So 0, 6 is one space away from the axis of symmetry, rather. If we go one space to the left of the axis of symmetry, you have a mirror image point. All right. So now we're going to talk about different forms of quadratic functions. So there's a couple different forms that you can put a quadratic function in. One form is called the general form of a quadratic function, and it is f of x equals ax squared plus bx plus c. Ax squared plus bx plus c, where a, b, and c are real numbers and a does not equal 0. So a, b, and c are real numbers. A is not 0. Now b can be 0, c can be 0, a cannot be 0. Now we also have a special form, and it is called standard form. I know it as this name, vertex form. That's how I learned it. So if I say vertex form, I mean standard form. So the standard form of a quadratic equation is f of x equals a parentheses x minus h squared plus k. So that this x minus h squared plus k with the a in front, that should bring back memories from transformations, right? Now, what's nice about this formula, this one right here, is that you can see the vertex. The vertex is h comma k. So h is the x coordinate of the vertex and k is the y coordinate of the vertex. So that's nice right there. So if I were to use general form instead, you would find the vertex this way. You would use this formula. H is equal to negative b over 2a. That gives you the x coordinate of the vertex. And then I'm not sure why they have this little a there, so I'm going to get rid of it. So if you want to find k, once you find h by doing negative b over 2a from the general form, if you want to find k, which is the y coordinate of the vertex, then you are going to substitute whatever it is that you found for h into the function. So you're going to substitute in your negative b over 2a into the function for x, and you're going to solve, and that will give you your k. And then you will have your vertex, because the vertex is hk. So let's do an example of that. Okay, so let's say I have y equals 3x squared minus 12x plus 2. Let's say I have that, and I'm sorry, you can barely see that too, but that does say squared. Okay, so if I were looking, this is general form, by the way. So if you remember, general form is y equals ax squared plus bx plus c. So I can go over here to the right and I can label what my a, my b, and my c are. So in this case, my a is 3, my b is negative 12, and my c is 2. If I want to find my vertex, which is hk, remember that h is equal to negative b over 2a. So I'm just going to substitute in b and a. So in this case, b was negative 12 and a was 3. So on top, I have negative 12, which is positive 12. On bottom, I have 2 times 3, which is 6. 12 divided by 6 is 2. So I know the x coordinate is 2 of my vertex. So now to find k, I'm going to substitute in what I just found into the function 3x squared minus 12x plus 2. And so we just found that the h was 2. So we're doing f of h, which is 2. So everywhere we saw an x, we're going to put in 2. So k equals 3 times 2 squared, which is 4, minus 2 times 12, which is 24, plus 2. So k equals 12 minus 24 plus 2. 12 minus 24 is negative 12 plus 2, which I believe is negative 10. It looks like my parabola has a vertex at 2, negative 10. And that also means that my axis of symmetry, I know that too, just from this. It is the equation x equals 2, because that's what the x coordinate is, 2, and that's where that vertical line is going to go through. Okay, so we're going to stop the video here because we're around 17 minutes, and we will pick up with part 2 of 5.1.